Hello and welcome to today's session. This session focuses on learning outcome for LO4. Understand the reactions of alcohols. In this video, we will explore how alcohols react in organic chemistry, examining their structure, reactivity, and the factors that influence their behavior. You will learn how different types of alcohols, primary, secondary, and tertiary, undergo specific reactions and why their classification matters. Alcohols contain the hydroxyl group, which is key to their properties. They are classified into primary, secondary, and tertiary based on carbon bonding. This classification impacts their reactivity, especially in oxidation. Primary alcohols have 1 carbon attached, secondary have 2, and tertiary have 3. Understanding this helps predict reactions. Alcohols combust similarly to alkanes and alkenes. In complete combustion, alcohol reacts with oxygen to form carbon dioxide and water. For example, ethanol burns cleanly, making it a useful fuel. This reaction highlights alcohol's potential as alternative energy sources. Their clean combustion is a significant advantage. Oxidation is crucial in alcohol reactions. Primary alcohols oxidize to aldehydes, then carboxylic acids. Secondary alcohols form ketones, while tertiary ones resist oxidation. Acidified potassium dichromate is a common oxidizing agent. Its color change indicates the reaction's progress. Alcohols can dehydrate to form alkenes. This elimination reaction requires heat and an acidic catalyst. For instance, ethanol converts to ethene and water. Dehydration is significant for synthesizing alkenes industrially. It involves removing a water molecule from the alcohol. Alcohols undergo substitution to form haloalkanes. The hydroxyl group is replaced by a halogen. Hydrogen bromide can facilitate this reaction. This process is vital for creating diverse organic compounds. Substitution reactions expand alcohol's chemical utility. Alcohols exhibit unique physical properties. Hydrogen bonding leads to higher boiling points. Short-chain alcohols mix well with water. As chain length increases, solubility decreases. These properties influence alcohol's applications. Oxidation conditions vary with alcohol type. Primary alcohols need gentle heating for aldehydes. Reflux conditions form carboxylic acids. Secondary alcohols oxidize to ketones under reflux. Tertiary alcohols resist oxidation due to their structure. Dehydration requires specific conditions. Concentrated sulfuric acid or aluminum oxide acts as catalysts. High temperature facilitates water removal. This reaction is crucial for producing alkenes. Conditions determine the reaction's efficiency. Substitution involves protonation and nucleophilic attack. Protonation improves the leaving group's quality. The nucleophile then replaces the hydroxyl group. Curly arrows depict electron movement. This mechanism is fundamental in organic synthesis. Ethanol dehydrates to ethene, showing primary alcohol behavior. Propan, 2-ol forms propene, illustrating secondary alcohol dehydration. Tertiary alcohols like 2-methylpropan, 2-ol dehydrate easily. This is due to stable intermediates. Examples highlight dehydration's versatility. Ethanol reacts with hydrogen bromide to form bromoethane. This showcases nucleophilic substitution. The hydroxyl group is replaced by bromine. This process is crucial for haloalkane production. Substitution reactions broaden alcohol's chemical applications. Alcohols are flammable and require careful handling. Some are toxic, necessitating safety measures. Use appropriate protective gear when working with alcohols. Proper storage minimizes fire risks. Awareness of hazards ensures safe laboratory practices. Alcohols have diverse applications. They serve as fuels and solvents. Antiseptic properties make them useful in healthcare. Industrially, alcohols are essential for synthesis. Their versatility makes them valuable in various fields. Understanding mechanisms is key in organic chemistry. Curly arrows illustrate electron movement. Protonation and nucleophilic attack are critical steps. Recognizing good leaving groups is essential. Mastery of mechanisms aids in predicting reactions. Reaction conditions dictate alcohol's behavior. Oxidation requires specific temperatures and catalysts. Dehydration needs acidic conditions and heat. Substitution relies on nucleophiles and protonation. Correct conditions ensure desired products. Primary alcohols oxidize to aldehydes and acids. Secondary ones form ketones, while tertiary resist oxidation. Dehydration produces alkenes, and substitution forms haloalkanes. Understanding these reactions is vital in organic chemistry. They highlight alcohol's chemical potential. Conclusion: alcohols exhibit a wide range of chemical reactions, each with significant implications in organic chemistry. Reactions such as oxidation, substitution, and elimination illustrate the versatility of alcohols and their ability to form various products. Developing a thorough understanding of these reactions not only strengthens foundational knowledge, but also enhances the ability to predict and manipulate chemical behavior in practical and theoretical contexts. Have questions? Send a WhatsApp to 07484361-688, and our team will be delighted to assist. Thanks for your attention, and see you next time.